So we're on page 183, and our goal is to uncover the factors of whatever the polynomial is. That is, what items multiplied together will get to the polynomial in question. Okay? And depending upon what you're given, there are different techniques or tricks that you might use depending upon how to factor, depending upon what you're given. Okay? There's patterns that we're going to learn about that if you recognize them, you'll be able to do a simple, easy trick to help you factor. And there's several of those patterns, but there's also some really simple stuff that will help you factor. First and foremost, if you can uncover the greatest common factor of a given polynomial and pull it out, you may have already factored it. Let's do an example and see what I mean by that. Example 1, and we're going to do A. 2x to the 4th minus 4x cubed plus 8x squared. This is why I like that other little technique of dividing out what they all share, because dividing out what they all share, in essence, brings you to factoring. Okay? The 2, the 4, and the 8, what numeric value can you divide out of all of those? A 2. Awesome. I'm going to just write that down. x4, x3, and x2. x2 is right. Okay? 2x squared can be pulled out of all of these. Okay? When dividing that out of these items, the result is x2 for the first one. The next one is negative 2x. And the last one is plus 4. Does that make sense so far? Okay. So based on that, I have pulled out the greatest common factor and I have factored this, okay, using the greatest common factor. The next one that I have, letter B, is 10ab cubed minus 15a squared b squared. We're going to do the same technique with this one, okay? I would say the numeric value that we're going to pull out is 5. And would you say ab squared on the letters? Okay, good. ab squared. So that is the largest thing that we can divide out of both of the terms in that binomial. In the first position, that leaves me with 2b. In the second position, that leaves me with 3a. I made my parentheses too big. Okay? Need to write it. Okay? That's the end of that. Now, you might say, well, how do I know that's the end of that? Well, that's where we get into the next section of our lesson, which is the patterns that I'm going to show you. We learned that when you have different things common, I'm going to go back and show you the chart I made way back when. We learned that when I have two things the same being squared, the result is that. Two things being subtracted being squared, the result is that one. Okay? We learned that if we are multiplying opposites, the result looks like that. Okay? What we're doing today is we're going to take this and go backwards and factor it to that. And I'll show you what I mean. At the bottom of page 183, it's got three different patterns. 2 patterns for what are called perfect squares, and 1 pattern for what is called the difference of squares. Okay? And depending upon what the product looks like, if you could recognize that it is related to one of these 3 patterns, you'll be able to go backwards and factor it. Easiest way to show it is to put my money where my mouth is, and let's just do them. Example 2. Stay with me, guys. This is going to bog you down if you don't practice. Z squared plus 6z plus 9. And if I say to you, let's factor it, your first step is going to be, is there anything that all 3 of these share? That was what I taught you in example 1. You're going to say no, there's nothing that all 3 of these share. Okay, are any of the patterns listed at the bottom of page 183 possibly represented here? Now, the easiest way to figure that out is like this. Is this a perfect square, yes or no? What's the square root of that? Z. I'm going to write it down. Is this a perfect square? What's the square root of that? 3. Awesome. So far I have Z and 3 written down. I'm going to throw it in parentheses for fun. If I take 3 and multiply it by Z, what do I get? If I double it, can I get 6Z? Then what must my sign be, positive or negative? That means that this item squared is the complete factor of that. Therefore, this is a perfect square trinomial. Okay? Why? Because this has a square root, this has a square root, and when those 2 things get multiplied together or and doubled, I get this. What do you mean get multiplied together and doubled? Well, go back and look at how a perfect square trinomial looks on page 183. On page 183, if you take the factored version and call this A and call the 3B, to get it to the product, A squared twice the product of A and B squared. Okay? That's how you go back and forth. You go from the product to the factors. A little more practice. We're going to do a little more practice. Letter B. B is 4s squared minus 4st plus t squared. Is there anything I can pull out of all 3? No. Okay? No, there's not. Let's see if there's any good patterns that we could recognize. I recognize square roots in the front and in the back. Square root of this is 2s. Square root of that is t. Notice I'm not putting a sign here yet. The sign, if this is indeed a perfect square trinomial, is relegated based on what the middle sign is. Okay? So the square root of that is that. The square root of t squared is t. If I multiply these 2 together and double it, I can get 4st negative. That means this also is a perfect square trinomial. Okay? The only difference between these 2 is that the center term is positive in the above, whereas the center term is negative in letter B. Okay? So those are a couple examples of perfect square trinomials. Letter C, this is my favorite because it happens to be the easiest. Letter C, 25x squared minus 16a squared. There's no third piece. There's only 2 pieces here. So, right off the bat, I know it's not a trinomial because it doesn't have 3 pieces. So, can it be the other pattern we've learned, otherwise known as the difference of squares? Well, let's see. Does 25x squared have a square root? 5x, right? Does 16a squared have a square root? Yes, it does. 4a. Okay, now if I simply make this positive or negative and square it, I have one of these two scenarios, and that'll create a trinomial. But if I make this 5x plus 4a and 5x minus 4a, I have what is known as the difference of two squares. This is the difference of two squares. Okay, there's two items in it. Okay, so whenever you see two items, automatically think, can this be the difference of two squares? Okay, the difference of squares. Okay, they don't call it two squares, but it's squares. Okay, now, moving on to example 3. Example 3 has us dealing with multiple steps to get to the final factored product, the final factor that you need. You're given something like 3x to the 5th minus 48x. Okay, this isn't a trinomial. It only has two parts. And it certainly can't be the difference of squares because it has a 3, which is not a perfect square, nor is 48x. Okay? But maybe we can factor something out and create a scenario where we get to the difference of squares. I am going to say, let's factor out 3x. Because then that would remove one of the x's from this, giving me an x to the 4th, which is indeed a perfect square. If I factor out 3x, I have x to the 4th minus 16. Okay? 3x times x to the 4th minus 16. This is indeed the difference of two perfect squares. That is a perfect square that has a square root of 2. That is a perfect square that has a square root of 4. So in order to create difference of squares, it's plus 4 and it's minus 4, all of that being multiplied by 3x. You with me so far? Maybe we're done. Maybe we're not. Can this be factored further? No, 3 times x. There's nothing else you can do. Is this a trinomial? No. Is this the difference of squares? No. Is that? So that becomes the square root plus the square root and the square root minus the square root. Bring down the stuff from above. And you have a fully factored version of that. It may seem tedious to get all the way down to this level, but if you quit right here, you're missing x plus 2x minus 2. Okay? Think of it like you're solving a puzzle. You got to get it all the way down to the absolute most factored form. And this cannot be factored any further. I can't pull anything out of this. I can't pull anything out of that. Okay? There's one other awesome pattern that I want to, or there's two, I should say. Two other awesome patterns, and they have to do with cubes. Okay? And that's the sum or difference of cubes. And you can see those about 2/3 of the way down, right above example 4. This scenario is if you recognize that you have a perfect cube being added to another perfect cube, then pull out the cube root of each. Okay, pull out the cube root of each, and then for this scenario, it becomes a squared minus ab plus b squared. Okay, sum of cubes, pull out the square roots, the cube roots, and then use these items to create this scenario, and it will be fully factored. Okay? In contrast, the difference of cubes, which is the next one I'm writing down. Pull out the cube roots again, only in subtraction form. And then what you have here, square it, multiply A and B together, square B squared, square the B. Okay? These